So looking at our dynamic address translation slide here, well, what was the motivation for this? Well, we wanted to start running multiple programs. We wanted to be able to overlap computation with I/O. And this really leads us to some form of multi-programming here. So we're going to want to run 2 programs at the same time. Now, note these 2 programs might be run by the same user at this point. We're not really talking about multi-user multi-programming. That's well, you probably want protection to do that. But right now, we'll just talk about translation. And one of the big challenges here is, so you want 2 programs to run. What happens if those 2 programs were linked at the same location? So they both want to run at the same location in memory. Or the data they want to access, when you statically link these things, is at the same location in memory. Well, that's kind of inconvenient. So one thing you can start to think about is actually have some notion of relocation. And you may not do this on a sort of chunk-by-chunk basis, but instead you do it on a program-by-program basis. So what you can do is you can have a base register so that all addresses that come out of, let's say, program 1 get added a certain offset to it. All addresses out of program 2 get added a certain offset to it. And all addresses that come out of the operating system have 0 added to them. OK, well then we can just change this base register, and they'll effectively move where our programs are. And we're going to call the address that when we start out that comes from our program the virtual address. And the physical address is where it actually is in physical memory. You could extend this a little bit and even actually add some notion of protection. So you could add something which says, program 2 here is only allowed to access up to this location, or this offset in itself. And past that point, it is not allowed to go access anything. Well, that's actually pretty easy to go do. And we're going to call that a bound register. Now, these base and these bound registers, we're going to look at it in more detail in a second. But you don't want the user program to go be able to change the base and the bound register. Because if the user program goes and changes the base and bound register, it can basically remap itself, or it can possibly make its bound big enough to go look at the other program. So let's go look at the hardware of a basic base and bound translation. So we have a program here, and it's going to do a untranslated address. That address is going to get added to it some base, and that's going to be the address you actually go to access your caches and your memory with. This address is compared to a bound register, and if it's bigger than some bound, it gets slapped on the hand, or it gets killed. You get some sort of violation. Now, this actually still shows up in modern day architectures, yet it's not super widely used. But in x86, you actually have segments, which have base and bound registers. So there's some problems with base and bound registers, which we'll talk about in a second. But otherwise, this works OK. You can have different segments. You can have programs that are basically relocatable by the operating system by setting this base register. You can protect memory by setting the bound register. And if the application tries to do anything outside of those parameters, it'll get killed. Questions so far? Sounds pretty good. One of the cool things you can do is you can have not only one set of base and bound registers, but you can actually think about having. Actually, before I move off the slide, I wanted to say something interesting here. What happens if you have 2 programs that want to share some data? can we do that here? That's definitely an option. You might want to share data and not code, or you might want to go the other way, which is actually more common, is you want to share code but not the data. So for instance, if modern Unix systems do this. They don't necessarily use this. They use it more of a page-based approach. But if you launch 100 copies of LS at the same time, the code for LS will be the same between all 100 different versions. So what you can do is you can actually point the base register at the same location and use the same piece of physical memory. So that's a nice little trick here, is you can basically share the same code segments between all your programs. And modern day systems actually do this. They share the code segments between all the same versions of the program. Obviously, if you have someone who's running version 1.2.7 of something, let's say LS, and someone else is running version 2.3.9 of LS, you can't share the code segment. But your OS will know that those are different codes. But if it is the exact same code, you can save a lot of memory by just only having one copy of it in RAM and not, 1,000 copies of it in RAM. So that's the big advantage of this separation. And in fact, this is actually used pretty recently. This is still, to some extent, vestiges of this, as I said, is in x86. But the old Cray vector supercomputers actually did not have a more advanced memory system, but but instead just had base and bound registers. And this was actually, to some extent, OK for something like a supercomputer, because supercomputers don't typically run lots of programs at the same time. They typically run one really big program. So it's a little bit easier in that setting than using an architecture like this for something like general purpose operating systems like your Linux desktop or something like that, or Windows desktop. OK, so let's take a look at how this fits into the pipeline here. So here's our pipeline. We want to add base and bound registers. It's actually not so bad. We have to add an adder here to add in the base into the program counter. And we have to add an adder for the data base register into all of our loads and stores. And then we need to add a comparator here, a comparator there to check to make sure we don't fall outside of our bounds. Now, one of the interesting things about this, though, is we're adding an extra adder. So you think this would slow down our clock frequency a lot. We're adding a whole nother, let's say, 32-bit wide adder. But conveniently, we already have an adder in this path. We already have an adder in this path. So the adder in this path is basically our PC+4 calculation. So while we do the PC+4, we can overlap that with the next addition. And you can actually have the carries basically happening at the same time. And the cost of it is only one extra carry delay out of a full adder. Similar sort of thing over here. It's kind of the same way that you would build a multiplier or something like that, where you actually overlap respective additions in the multiplier concurrently. So it's kind of nice that you can do this relatively low cost. To some extent, it just sort of melts away. You can even go faster. I think this note here, we talk about carry save adders. You can also do carry select adders, which are even faster, where you just have basically one bit that tells whether the last bit carries or not. But you can go quite fast here. OK, so let's talk about the challenges of base and bound. So let's say we have memory here. And we start off with 3 processes: user 1, user 2, user 3. User 1 is 16 kilobytes. User 2 is 24 kilobytes. User 3 is 32 kilobytes. And this is just some open space, free space here and here. So all of a sudden, more users show up, and they start to run some processes. User 4 goes here and fills in this space here. User 5 goes down there because it can't fit in this 8 kilobyte segment. So 8 kilobyte segment or 8 kilobytes free space here and has to go down here. OK, that's all well and good. 2 and 3 kill their programs. They stop running their programs. So all of a sudden, this goes away. Or excuse me, 2 and 5 goes away, and this one goes away. So we start to get some holes showing up here, and some small holes. And if you repeat this sort of thousands and thousands of times, at some point, with relatively high probability, you end up with lots of little chunks of memory, which are hard to go reclaim. And this is memory fragmentation. If you go look at something like a modern-day garbage collector, it'll actually try to re-squish all this data together. But that's hard to do when a program's running. It's hard to go take these other programs and go re-squish them. It's also possible that, depending on how the addresses are laid out, you just may not be able to go do that. If you have base and bound, it's possible that you might actually be able to go move the data, but you'd have to go copy all of the data. And that takes time if you have to copy your entire memory system. This is why something like garbage collectors can be pretty inconvenient, because some of the garbage collectors actually require you to go copy everything. There's a couple different techniques you probably talked about in your data structures class about how to go do efficient garbage collectors. But let's say we just want to avoid this completely. So can we go avoid this?